Hi, good afternoon, everyone. My name is Patricia Jordan, and I'm a regional marketing manager at Interface Engineering in the Washington, D.C. office. Thank you for logging in today, and welcome to the fourth installment of our 2026 High Performance Buildings Educational Series, Radon Mitigation Design, Passive and Active Strategies, presented by Steve Dacus, Principal at Interface Engineering, and Jeff Humphreys, Principal at McKinsey. This webinar will examine the codes, standards, and regulatory requirements that inform radon mitigation design. All the participants will learn about key guidance documents, testing considerations, and best practices that support healthier indoor environments and compliance with applicable requirements. Before we get started, we have some housekeeping notes. Interface Engineering is an approved AIA CES provider, and this is an AIA accredited course. For today's participation, you'll earn one learning unit, health, safety, and wellness credit. All attendees will either receive a course completion certificate, or if we have your AIA number, attendance will be reported to AIA for you within the next 2 weeks. We are using a GoToMeeting platform, so all audience microphones will be muted during the presentation. However, please feel free to enter any questions into the questions field. There are 2 versions of GoToWebinar, so depending on the version you selected, the question field is either on the top bar with a chat box and question mark, or it needs to be popped out of the control panel. We'll leave about 10 or 15 minutes at the end of the presentation to answer any questions. If we do not get to some of the questions posted, we'll make sure to distribute a Q&A summary to all. And today's presentation will be recorded and made available through our website and YouTube channel. We are thrilled to welcome you to today's webinar, and please join me in welcoming Steve and Jeff.
Awesome. Thanks, Patricia. Hi, my name is Jeff Humphreys. I'm an architect. I'm one of the principals at McKinsey. McKinsey is an integrated design firm. We have structural engineering, architects, civil engineering in-house. We're predominantly a West Coast firm. We do work all across the country, and I head up our civic work. So we do a lot of public safety and municipal projects.
Yeah, I'm Steve Dacus with Interface Engineering. I'm based out of our Portland, Oregon office. Been designing HVAC systems for almost 33 years now. I'm a principal and team leader here in the Portland office. So me and Jeff have been working together for many years on different types of buildings. And it's great to be presenting with Jeff on this.
Yeah, like Steve said, we've both have been in the industry for over 30 years and probably worked together for like 25 or so. We've worked on a variety of different project types, but over the last 20 plus years, it's really been civic and public safety projects. In fact, the last few projects that we've worked on, we've been able to show compliance with radon mitigation through alternative means or what are the exceptions that's outlined by the code. And in the last few projects we've had, that wasn't the case. We weren't able to do that. We actually had to install systems that would mitigate radon. And so we thought it was really important for us to bone up on the topic so that both of our teams were better prepared for the current and future projects. And that is the genesis for why we developed this webinar.
So as part of our AIA accreditation, we've got a course description here that outlines this presentation. We're going to introduce radon gas and its health impacts and the importance of designing radon mitigation systems for that built environment. Hopefully you gain a foundational understanding of what radon is, how it enters the building, and why it poses a significant risk to occupants and how we can address that. We're going to review applicable codes and regulations and help you understand the regulatory expectations and design best practices. We also have these learning objectives We anticipate you're going to learn about what radon gas is and the importance of designing systems to remove it. You're going to learn the different codes and guidelines that describe radon mitigation strategies. There's two different types of radon mitigation strategies that we're going to describe to you and show you, and we're going to describe the advantages and disadvantages of both of those. And then finally, just learn about the construction of these strategies and all the components that go into this. Here's our agenda for today. First off, we're going to talk about the prevalence of radon and its dangers. We'll go through design guides and the regulatory requirements that we have. What can we do as a design professional? We're going to ask ourselves that and what we can do as design professionals. The two types of systems, we'll get into the nitty-gritty there on active and passive radon design. And then finally, we're going to summarize what we've presented, as well as go through an example project.
Great. So let's dig into it. So what is radon? Radon gas is it's a natural occurring gas. It's a radioactive gas, and it forms when there's a breakdown of uranium, thorium, or radium, which are radioactive materials. And when they break down in rocks, and soil, and groundwater, that can be released as this radioactive gas, this radon gas. It is not a localized thing. This is something that is, we'll show here in just a minute, a map of the United States. It occurs all across the United States. Here you can see the hot zones for where you have the highest exposure and concentrations of radon. And it is worldwide. It's not just the United States or a North American continent thing. This is a map that's distributed by the US EPA. I think one of the things you can see here is there are a lot of states that are touched that have high concentrations of radon in it. As we were putting this presentation together, it's interesting to find that there are only 18 states that actually require radon mitigation as part of the building code. And there are clearly more than 18 states that are impacted with this high exposure of radon. Our presentation is going to focus largely in the Pacific Northwest, where we do work in Oregon and Washington. So if we go to the next slide, this is a map of, okay, sorry for the hesitation there. This is a map of Oregon. And so this is based on testing. And so here you can see the concentrations. It's a little bit different map than what you saw from the US EPA. But you can still see the higher concentrations. Pretty difficult to kind of figure out where your project would be and whether or not it fell into one of these categories. And so the building code decided that they were going to simplify it and identify it by county. And so in the state of Oregon, if you're working on a project that fits the criteria, and the criteria is it an R2 or an R3 occupancy, or is it a public building? If it falls into one of these 7 counties, you will have to meet the requirements for radon mitigation. And then if we go to the next slide, this is the state of Washington, and this is based on samplings that they have. And I'll take a moment here, I didn't say it before, but the US EPA, they distribute dollars to all states, and those states have different organizations. So this organization, the Washington State Department of Health, they are in control of receipt of the dollars that they get from the EPA. And they can distribute those dollars how they see fit. And some states, that is actually testing. They'll distribute tests. So in the state of Washington, if you wanted to get a free test, you'd contact the Washington State Department of Health, and they'll actually send one to you if no sampling has been done in the area of where your project is actually at. It's similar for Oregon as well. So this is the map. Again, if you look at the geology of it, it's kind of all over the place. It's not following county lines or anything like that. If you go to the next map, they followed a similar suit, the state of Oregon. And what they did is they broke it down by county. It just so happens it's also 7. So if your project fits the criteria, which in the state of Washington is an R occupancy, and you are in one of these counties, you will be required to show that you meet the requirements for radon mitigation. Next slide. Okay, so now we've shown it's a naturally occurring and it's prevalent across the country. There are a lot of hazards associated with radon. The biggest one is lung cancer. Emphysema is another one, chronic obtrusive pulmonary disease. There are other respiratory issues and other links to cancer, all as a result of exposure to radon. And if we go to the next slide. So radon exposure is the second leading cause of cancer next to smoking. And if you look on the right, this is another chart here distributed by the EPA. So that was very interesting. There are more deaths every year, 21,000 deaths as a result of radon exposure, and that's more than the amount of people that are killed in drunk driving accidents. Go to the next slide.
So you may ask, how does radon enter a building? Well, there's many different ways of doing it, but the driver for most of that is the pressurization within our buildings. A lot of our buildings have different forms of exhaust, whether it's from kitchens, bathrooms, restrooms. They create negative pressure zones or negative pressure areas. And if we don't have enough makeup air for these spaces, then this radon gas can come up through cracks in building assemblies, for example, where the slab meets the exterior walls, the joints between building materials, even interior walls where they may have gaps there. That air movement from that negative pressure inside the building can draw the gas up from the soil below. And then any sort of water vapor, any moisture that could seep into a building in a basement or through a slab, that could also contain radon gas, and that could get into the building through that method. So let's go through some of the guides and regulatory requirements. Sometimes I'm asked, hey, can we test a building site, a raw building site, before we ever started construction to see if radon is even present? And that's not possible. Radon has to have something to trap it, an actual building, for example, to have the gas seep out of the soil and into the structure, so then you can actually test it. Otherwise, if it's just open to air, you can't test it in real concentrations. However, like Jeff was alluding to, there are tests available for existing buildings. You can go to your big box home improvement stores, and they are there on the shelf. You can buy those. You can put these, they're a little cylindrical metal disc that you place in the space that you're trying to test for 2 days, 3 days. Then once you're done, you take that disc, you put it in an envelope, and you send it off to a testing agency, and then they send you back the report. So there is that testing available to anybody that wants to do it. The EPA does publish some standards online. If you look, they have radon standards of practice on their website. It mostly addresses residential construction, but that is there as a guide. ANSI and the American Association of Radon Scientists and Technologists have published a standard also. It was published in 2018 or revised in 2020. It's radon mitigation standards for schools and large buildings. It's not very prescriptive. It talks in many generalities, but it does have some guidelines for radon mitigation. The best that we've seen for prescriptive requirements is the Oregon Structural Specialty Code, the building code for Oregon State. In Chapter 18, Section 1811 and 1812, there are prescriptive requirements for radon mitigation. And again, for new public buildings, it's required in Oregon, as well as R2 and R3 occupancies. And then Washington State Building Code, the 2021 version, Chapter 12, Section 1202.7.3 also lays out requirements for radon mitigation for residential occupancies only in the state of Washington.
And the references that we're going to be focusing on today are based on the Oregon Structural Specialty Code and the Washington State Building Code. But a lot of what you'll see in today's webinar will be applicable in your own jurisdiction. You need to look at your own code and look at how these things are going to apply to what your code is. And we had a webinar earlier today, and there were some attendees from Florida. Steve and I looked briefly at the Florida Building Code, and there were several references and items that were very similar to what we have in Oregon. So I think even though you may be calling in from a different state or have a project in a different state, some of this material you might find is appropriate and applicable to your project. A couple of things that's interesting about radon, it's not a new occurrence. It's been around for the longest time, but I would say that the building codes have slowly been warming up to like, we should probably do something about this. When we were doing the research associated with this, we found a few different things. A few of the first states that actually implemented the first requirements for radon mitigation included New Jersey, the state of Oregon, and the state of Washington. And this is fairly recent. So New Jersey, they just started implementing requirements in the 90s. In the state of Washington, there was Washington Administrative Code requirements. That's not building code. That is their state law that went into effect in 1993. But they didn't adopt the IBC's Appendix F until 2007. And in the state of Oregon, there was a Senate Bill 1025. It was passed in 2010, and it went into effect on April 1st, 2011. And that first requirement was for R2 and R3 occupancies only. And then the following year, they implemented it for all public buildings as well. So a relatively new occurrence for these requirements. And then Steve and I were reflecting back on it. And even though they were in the building code, it was something that wasn't heavily focused on or enforced until more recent times. Oh wait, Steve, maybe one more thing I could jump in on there.
Yeah.
We were also going to share that even if radon mitigation is not required in your location, if you go to the EPA, we gave the QR code on it, and you look at the map associated with that, or your agency within the state, and you look at the map on it, and there's a high concentration of radon, it's probably worthwhile to implement strategies to reduce or eliminate radon accumulation in your building. It's a small cost, and the grand scheme of what the project cost is going to be to implement. We have clients that have had litigation issues in the past, and when we start the project, we ask the question: would you like to implement radon mitigation, even though it's not required by code? And the response is yes. We don't want to go through that again. Let's go ahead and put in the system so that we're prepared.
Yeah, so asking the question, what can I do as a design professional? First steps are to do that is to confirm your regulatory requirements for your jurisdiction, that you have a building or new construction going on. What are the local code requirements? Like Jeff is saying, well, there may not be any specific requirements, but if someone wants this voluntarily, then what standards do we use? Do we use the Oregon Structural Specialty Code? Do we use something that's in a nearby jurisdiction? Next, the decision needs to be made whether it's a passive system or an active system. And then on EPA's website, they talk about integrating radon-resistant new construction techniques, and we're going to go through some of that in some of these slides, but how do we incorporate those things into our design? And then the question still remains, are there exceptions to this? Even though it may be required, there are some exceptions to some of the codes. For example, the Oregon Structural Specialty Code in Section 1811 has certain building types that are exempt. Some of these kind of make sense. Temporary structures, greenhouses, open-air grandstands, farm structures, buildings that are Group S, H, and U occupancies, an elevated building where you don't even really have contact with the ground itself. But then in addition to that, for HVAC systems, if you have certain HVAC systems that meet this criteria, they can also be exempted. So you have to have a minimum of 20% outside air that's delivered through a mixed air system that's delivering 6 air changes per hour or 1 CFM per square foot of supply air. I mentioned about mixed air systems, but this method is also allowed under that ANSI and AARST standard that I mentioned a couple slides ago. That 6 air changes or 1 CFM per square foot is pretty standard for many buildings as a mixed air system. So mixed air meaning outside air mixes with return air to be the total supply air, the total 6 air changes per hour, 1 CFM per square foot that's actually delivered to spaces. But we deal a lot nowadays with dedicated outside air systems or DOAS systems, and those are 100% outside air systems that are used to treat ventilation air only in conjunction with a separate system that provides space cooling or space heating. So if you took this criteria of 20% outside air, so of that 1 CFM a square foot, for example, that's being delivered to a space, if 20% of that is outside air and you're using a dedicated outside air system, it follows that those dedicated outside air systems should have a minimum of 0.2 of a CFM per square foot. So we're getting now into the passive and active radon systems and what is incorporated in those. And before we get there, we need to talk about some of the terminology that we're going to be using.
Yeah, the codes have introduced new terminology and acronyms and abbreviations that can be a little bit hard to follow when you're sorting through the code. And so taking the time to go through that, we thought it would be advantageous. So we got the next few slides here. We're going to talk through, regardless of which system, active or passive, these would be applicable to it. So the entire system for radon mitigation is called a gas conveyance piping system, or a GCPS system. And there's a few different components. This is a plan view. We're showing the soil gas collector pipes. Those are the pipes that are in the suction zone. They're below slab. And then we're also calling out the riser, which is the SSESD, or the sub-slab soil exhaust system duct. You got to wonder who comes up with these terminologies. So they're tongue twisters of descriptions. But anyway, that's a plan view of the things that occur below the slab. And then looking at that riser in kind of an elevation view here, you can see that bottom line there. You can see the soil gas collector pipes. Above that will be that soil gas retarder membrane. That's preventing the gas from seeping from the soil up through the slab. And then we've got the slab, in this case, slab on grade. And then we have that SSESD, or the sub-slab soil exhaust system duct, and that runs all the way up and then penetrates through where the roof line is actually at. And if we go to the next slide, we developed, oh, sorry, this is you, Steve.
Yeah, that's fine. I know you probably could speak to this slide too, but yeah, these are 2 different details that we would provide on our design, one for Oregon, one for Washington. The biggest difference here is the references in the detail notes to the specific code sections for those 2 states. Key thing to note is that this shows an active system, so there is an inline exhaust fan that's provided for that SSESD as it goes from below grade or below the slab up through the roof and then out the building. This is similar to that diagram that we showed previously, but it shows what we need to do, or the systems that we employ from an HVAC side of things, to create a positive environment in the building as compared to the subsoil space. So we have our HVAC systems like we talked about. We're bringing in outside air, so that naturally pressurizes our buildings. If we have an active soil depressurization system, or we're negatively pressurizing the below slab portion of the building, then we've created that pressure differential. So radon gas won't go up into the building. It's going to be sucked into that active system and then exhausted out of the building. This diagram is based upon one of those older documents. Like Jeff said, this has been around for a while. So this diagram is pulled from a 1994 document from the Environmental Protection Agency, where they gave guidelines for schools and large commercial buildings.
So we are going to be getting into the focus of active and passive systems, but before we do that, we wanted to talk about kind of the foundation zone and the design of the elements associated with that area. And so we're going to be talking about the membrane and what we need to do with this membrane. So the next couple of slides here kind of break down some pieces associated with this. So on this first one, we're going to toggle through these. So starting at the top, we have our slab on grade. In this case, you may actually have a situation where it's a crawl space, but looking at kind of more common commercial application, this is generally what you're going to see. Code requirements are for that slab. Are there any cracks? Are there any joints? Are there any seams? All of that has to be sealed, so nothing can actually permeate through the concrete. And then highlighted now is that soil gas retarder membrane. So any seams within that membrane have to be lapped by a minimum of 12 inches. They need to be taped so they're sealed off. Any penetrations, pipes, conduits that are coming up out of that, those also need to be sealed off. If there are any tears or cuts that occur as a result of when it was installed, those would have to be addressed as well. And then in this zone right here, this is the suction zone. This is where the pipes would actually be. They're collecting all the radon gas and they migrate up. And so that's in between that soil gas retarder membrane and then the geotextile fabric, which is the next slide. And so that's usually more of a structural element separating the slab out from your structural base. So if you go to the next slide, this is going to be generally is dictated by the geotech. And so this is our pad. This is usually in the neighborhood of 6 to 12 inches in thickness. And it's usually compacted with small fines in it. And so it's difficult to get gas to actually seep through that. That's why we have that suction zone up above that. It is possible, however, that you may be able to work with your geotech. And if you can't combine those two elements, you might be able to play with the thicknesses associated with those. But that suction zone, there's code stipulations of minimum cover over the top of the piping that's actually in there. That's usually 2 inches. And so that starts to dictate a certain height that's on there. And so that assembly might be fairly thick once you make through all those different pieces. Okay, that's it. And then, so that's just kind of looking at the assembly top to bottom. So we talked about the gas retarder membrane, and it has to be sealed off. Well, it also has to be sealed off where it terminates up against the foundational wall. So on the right side here, we're showing a concrete foundation and a footing wall on it, or footing. And then you can see the slab that comes over, and there's a little bit of a bench for the slab on grade to actually set on the foundation wall and butt right up against it. And so in this particular case, you can see the soil gas vapor retarder is actually running along the bottom of that slab, and it comes over and it's sealed up against that step and that foundation wall. So it's sealed off with tape for the membrane manufacturer's requirements. And so that creates that tight fit there. On the left side, that is a different application where you have CMU block. And a lot of times when we use CMU block, we fill all the cores on it. And so it's still solid. But when we were looking at Florida state requirements, if you have a CMU block wall and it's not filled in there, that is considered to be a permeable area. So you wouldn't be able to seal off your membrane to that CMU block if it was a regular block and you didn't have the concrete that was actually in it. So, but in this case, that membrane goes over, it's turned up the CMU block, sealed, and then the slab is poured up against it. And so that's how we handled these two different applications of terminating the membrane. And then we go to the next slide. So we talked about the pipes coming together in a spot. Centralized plenum box is one description that's described there. It is a void, and so you need to create a spot that is going to be able to have your slab on grade span over until it cures and have a void underneath it. And so in this particular case, we kind of borrowed from the EPA guidelines, this idea of having CMU blocks that are 8x8s that create this void. And the size of this thing is actually stipulated by code. And so in the state of Oregon, it's 2 feet by 2 feet. And I believe the minimum thickness or depth of it was 8 inches. So we basically hit that criteria with this. We have structural in-house. When we went through this detail, trying to develop a standard detail, they wanted to thicken the slab where it spans over this. And so that's what you can see there with the reinforcing and the change in thickness there. I think that those are the things that I wanted to highlight. Sorry, go back to that. Where that void is, that's where the pipes come together. And then you can see on the top plan view there, it tees over to the riser, which is that SSESD that vents up to the roof. Now we can go to the next slide. So in the state of Oregon, this is not outlined in Washington, but again, I did also look in Florida, and Florida also has similar criteria. So in the state of Oregon, they have 3 different levels of cracks that you might see in your slab. Concrete is probably going to crack, right? Some level of cracks. The hairline cracks that are 1/16 of an inch or smaller in size, in the state of Oregon, they can be left as is. In Florida, when I was looking at that, they actually expect you to grind it out to a 1/4 inch width and a 1/4 inch depth minimum, and then fill it with elastomeric sealant. In the state of Oregon, crack 2, if it's greater than 1/16 of an inch, then that's what you would have to do. You'd have to grind it out so that it's a minimum of a 1/4 inch wide and a 1/4 inch deep, and fill it with elastomeric sealant. And then the last category on the left there is if it's greater than a 1/4 of an inch, or there's any vertical displacement between that crack, you would actually, again, have to grind it out so that it's consistent thickness and consistent depth. And then you'd apply your elastomeric sealant in there so that gas would not be able to pass through that. I think that's important to note on here, because in the past we've had situations where you choose not to actually have joints, whether it's an expansion joint or a control joint or pourbacks for structural elements. All in this needs to be sealed. You can't just leave concrete tight against one another. It's code required that actually any cracks or joints are actually going to be sealed. And then also in the state of Oregon, it actually has to have a special inspection. All the cracks, the slab has to be inspected and signed off before any finished flooring material can be installed.
Great. So those are things that have to happen no matter what the type of system is, whether it's an active system or a passive system. And these are some requirements for the mechanical system that also don't matter whether it's an active system or a passive system. So that any piping or duct that goes above grade has to be sloped back to below grade, and it has to be labeled with something on it, whether it says radon vent, quote unquote, radon reduction system, quote unquote, or some other distinguishing tag, so that it can be distinguished, that pipe can be distinguished between other HVAC or plumbing systems, such as vent pipes or hydronic piping or anything like that. Obviously, we want to have the piping sealed above grade. So if we want to seal cracks and penetrations to membranes, we obviously want any sort of pathway like a duct or pipe that's going through the slab to also be completely sealed, so that gas doesn't come up through that piping and then go into the occupied space. It must be compatible with the construction. So if you have a return air plenum or a supply air plenum, PVC is not allowed in those plenums. So metallic ducts are perfectly fine to have above grade and go into or then go through construction and go through the building to the exterior. That's perfectly fine as long as it meets the same area criteria as the piping that's dictated by code. And then a T-fitting is mentioned in some of the codes as a termination, and as long as the piping is directed away from inlets or openings. The picture on the right side of the screen shows an exhaust fan with the discharge going straight up, away from the roof, away from any sort of opening like that door that's in the background. And these terminations have to be a minimum of 12 inches above the roof and 10 feet away from those openings or any mechanical intake for outside air. This diagram on the right-hand side of the screen is a very good diagram. It's in the Oregon Structural Specialty Code for passive depressurization systems. It shows a network or a tree of 3 or 4 inch perforated PVC pipes or gas conveyance piping systems that are spaced every 50 feet maximum. And then the termination or the end of the pipe can be no more than 5 feet from the perimeter or foundation wall. That is within a trench. It's dictated by code, again, 12 inches by 8 inches deep. So if you've got a 3-4 inch perforated pipe, that'll give you that cover that Jeff was just talking about. And then that goes to a single SS ESD for every 2,000 square feet of area with a plenum box. So that's key to note, is that this passive system can serve up to 2,000 square feet of floor area. And even though it's a passive system, it doesn't have a fan. You do have to provide provisions for a fan to be added in the future. This is a good section or cross-sectional view of that. Again, the below slab or the slab prep is, as we talked about, the spacing of the network across the slab or below the slab is noted below or in the previous slide. We have to have one separate riser for each below slab volume. So if there are stem walls or below grade foundation walls that divide up a footprint into smaller volumes, then that means you have to have a separate system and a separate riser for each one of those below slab volumes. And the codes, again, differ in some instances. For Washington, a passive system you can have as small as a 3-inch PVC pipe going to the exterior of the building. In Oregon, it's 6 inches. So again, there's that difference between the two codes, and so it's very important to understand your jurisdiction and where the project is, what those requirements are. Also, you can see on this section on the left where the provisions are made for a future inline exhaust fan. There's a junction box that must be provided either in the ceiling space or the upper floor or in an attic space, and then that can be connected to an inline exhaust fan in the future if necessary.
I know a lot of firms like to try to develop standard details so they fit for all the applications that you can. And so McKinsey's not different than that. We tried to do the same thing. And seeing differences between the Oregon and Washington code, we basically picked the more stringent and went with that, and just went with the idea that we're going to apply this on either projects if they fit in these states. And so with that, this SSESD, or the vent pipe that runs up to the roof, it's a 6-inch pipe dictated by Oregon. And if you have concerns of sound transmission from one space to another and you're trying to bury this thing in a wall, it's a pretty thick wall, right? In order to have the pipe and then the pipe insulation around it, any sound attenuation insulation in that wall cavity, it's like, just think about it when you're trying to locate that, because it's not a small thing.
So up till now, we talked about passive systems. Now we're moving on into the active systems. Like we said, the below grade stuff is exactly the same or very, very similar to a passive system. A single riser from a pit or plenum box, a T-fitting at that entrance to that pit or plenum box. The single riser that we're talking about now, it can serve up to 4,000 square feet though, if it's an active system. And then if you combine that with the passive system network in Oregon with that maximum of 50-foot spacing and the 3 or 4 inch perforated pipe tree that's underneath your slab, and if that becomes an active system where you have an exhaust fan tied to it, that can actually serve up to 15,000 square feet of floor area. Again, we're talking about a 6-inch PVC riser from that plenum box or below grade. And then same things apply for an active system as a passive system. If you have those below grade segregations, those foundation walls or stem walls or something that divides below slab volumes, then you have to have separate risers for each one of those volumes. And the termination requirements, again, are very, very simple, very straightforward. You cannot direct that exhaust towards any outside air intake. You have to maintain 10 feet. The photos here on this are of an actual project that we did with McKinsey, where we had, as you can see, 4 different zones over a floor plate of roughly 15,000 square feet. So using that 4,000 square foot rule of thumb, we still had to have 4 different zones, 4 different piping networks connected to these 4 different inline exhaust fans. You can see that the piping is labeled there. It's labeled as radon gas, so everybody can see in this mechanical room where this was located that that's what these systems serve. And then if you go up to the roof, that's what you see is these T's with those 45-degree chamfers on each end of the piping. And these are located well away from any sort of outside air intakes or any entrance into the building. So we're going to summarize what we've gone through here, as well as go through some project examples or an example project. So understand that the slab and under slab, there is a membrane that we have to maintain. We have to seal any penetrations. That goes for piping, that goes for conduit. That's anything that goes through that membrane, through that slab, has to be sealed. Any tears or cuts in that membrane have to be repaired. I was actually talking to an envelope consultant about how they sometimes even require this membrane to be pressurized underneath it and air blown up before the concrete slab is poured, just to make sure that the integrity of that membrane is there. Jeff talked about sealing the cracks in the concrete slab, sealing the joints in that concrete slab, as well as the transitions from the concrete slab to our exterior walls, making sure that that seal is continuous there. And then, of course, within that suction zone, that aggregate layer, we need to have our 3-inch or 4-inch perforated PVC pipes so that we can collect all the gases to our plenum box or to our SS ESD. So then it goes directly from below the slab and out of the building to the roof. If it's a passive system, we won't have a fan, but we have provisions for a fan. And if we have a fan, we want to locate it as high up as possible so it's accessible, but yet it's depressurizing that section of below slab and then gets any sort of radon gas out of the building and through the roof. And then obviously the termination has to be at the exterior of the building. So here's an example of a 6,000 square foot footprint. If we have that broken down, we're going with a passive system. We're limited to 2,000 square feet, right, of that, barring any sort of other walls or below slab walls or foundation walls that we need to, that would divide that up even further. So each one of those zones has that piping network spaced no more than 50 feet. The ends are within 5 feet of the perimeter. They go to a plenum box. Then there's the riser, a solid PVC pipe that goes to the exterior of the building. It's a passive system, but we do have to provide that provision for a future exhaust fan. So a 6,000 square foot footprint has to be divided into three zones if we're looking at a passive system, according to Oregon's requirements. Now, if we have an active system, our maximum square footage goes up, doubles. It goes to 4,000 square feet. So this 6,000 square foot example, now we only need 2 zones, and we don't need that network, that spider web of perforated pipes. We just need a collection area, a single 24 by 24 by 8-inch deep plenum box, and then that riser, that SSESD, goes from that plenum box or that collection point up through the roof, through the inline exhaust fan, and to the termination. Now, this is the example that I was touching on when I was going through the active system. So if you want a hybrid system that has, you have the piping network, you have the perforated 3 or 4-inch perforated pipes, no more than 50 feet on center. They all come back to a riser. You don't have to have a plenum box if they're all connected to this single 6-inch PVC riser. Then you can serve up to 15,000 square feet of floor area. So in this case, we'd only need one of these risers with this network of below slab piping. So let's summarize the advantages and disadvantages of both these active and passive systems. The advantages of the passive system, of course, there's no mechanical devices. We don't have to have an exhaust fan that may fail. It's a simple system. It's all piping, rock, the ceiling, the concrete, everything like that is relatively simple. The disadvantages of that are, of course, the larger amount of underground piping. You do have to have a provision for an exhaust fan in the future. And then it does serve a smaller system or smaller area than an active system. So going to the active system, that's the big advantage, right? You have less underground piping. It's a larger area with a single riser. It's potentially less cost. It could be less cost given the trenching, the aggregate, the piping network that has to be in place with a passive system versus the active system. It could be very well less expensive with the active system. Of course, we do have that mechanical device, that electrical connection to that exhaust fan, the exhaust fan that runs. It has to be set so that there's an alarm if it does fail. So it should run continuously. But for whatever reason, if the fan fails to operate, then an alarm has to be generated so somebody can investigate. And you can't investigate if you don't have access. So you need access to that fan somehow, some way. You just can't bury it somewhere and forget about it. So that concludes our presentation. We've got about 12 minutes to the hour. Have there been any questions that have come in, Patricia?
Yes, there are a couple questions here that I'll read out to you.
Okay.
The first one was, do you have an example of a thickened edge slab on grade termination detail? Or can we provide one of those?
You want me to go back, maybe, Jeff, to that?
No, you can, but those are
or
not thickened slab.
Okay. Yeah, there's not really anything there, I don't think, right?
Yeah, that's an interesting question. On a current project we have, I can't think of how we are currently terminating it, but we do have thickened slab where we have, I think, some overhead doors. I'll have to look at that. So in Oregon, we have to do perimeter insulation, and I'm thinking that what we will probably do in a thickened slab would be we would go down this, under the slab, we would go down the drop for the thickened slab edge up and bring it up the other side of the face, so it kind of goes around, and that's where your perimeter insulation is going to be. So I kind of feel like that's the way that would be done, but I don't have a visual to show you, just what I just described.
Okay.
There's a few more questions. The next one is, what is Oregon's attitude about saw cut control joints in SOG? We need to enlarge all control joints to 1/4 inch and seal? ?
Good question. Okay, so the crack control is a saw cut. It's whatever the thickness of a saw blade, and it goes down X amount to try to dictate that's where the slab is going to crack. That is an interesting question. I had not thought about that yet, because we're saying we want the slab to crack there. So when the slab does crack there, that means that's a place for the radon to actually get through. So I actually haven't seen this actually come up yet, but I'm kind of feeling like you hit a spot of like, yeah, that's probably not permissible. The joint at the top would need to be a 1/4 inch wide, and it would need to be a 1/4 inch deep to be sealed to meet that crack number 2 category. Which would be an expense associated with that. And our public safety projects that we work on, fire stations, we used to do the apparatus bay as a really thick slab that went all the way through there to handle the weight of the vehicles that are in there. And a lot of times we'd have the question with the client of like, do you want us to seal the control joints, or do you want us to leave them open? And it became more of a sightliness. It was like, because you're going to get dirt that accumulates in there. I take that to be the same thing. It's not an option anymore. So now we're actually going to have to seal all those joints.
Mm-hmm.
Okay, the
And
next
maybe one
question.
thing to note.
Oh, sorry.
Sorry to interrupt, Patricia, but one thing to note is we're really only talking about occupiable spaces.
Yeah, it's true.
So occupied spaces. So an example like you just brought up, Jeff,
Probably
like that wouldn't
fly.
have a radon mitigation system that's in an apparatus bay or a large warehouse or something like that that's not regularly occupied. We're only talking about spaces that would be occupied by people.
Good point.
Too.
Yeah, you're right. You're right.
Okay, the next question is, in residential construction with a crawl space, would an active ventilation fan installed in the crawl space be sufficient to minimize radon infiltration into the home?
Yes, absolutely. That's definitely something that the codes, they actually do dictate that, or there are some prescriptive requirements in Oregon for crawl spaces. But yeah, that's exactly what would be done for more of a residential type construction where you do have a crawl space. You'd have that radon, the SSESD that goes into your crawl space and then goes through the floors above. If it's an active system, then you have a fan. If it's a passive system, you wouldn't, but then it goes to the exterior of the building. So yes, you would definitely have something in the crawl space. We limited our presentation here. So go ahead, Jeff.
Oh, I was just going to say, I was just thinking somewhat related, that as anybody that's working in residential design or as a homeowner, when we were putting this material together, I didn't realize this. When we moved into our house, I did radon testing. It looked good. I'm like, all right, cool. Don't need to do that ever again. The EPA recommends radon testing every 2 years because conditions change. And I was like, oh, that's an eye opener. I did not realize that.
Right. Yep.
I'm not sure if this is just a take on the same question, but this says in Portland, a lot of SF homes have a shelf basement where part of the basement is open to a crawl space. How does the crawl space affect the plan?
I think it still has to be ventilated. I grew up in a home that was it was pretty old. I think it was built in just the turn of the 20th century, and it had that. The basement, I mean, you could literally look in the basement where our laundry room or where our laundry utilities were. You could literally see dirt up above on a shelf. It was probably 3 or 4 feet high, concrete, and just dirt and posts and beams. You can literally see right through there. So definitely that's the case. And obviously, we want a vapor barrier. You want all these membranes to be in place, but then also exhaust those. Also, the radon testing, that would be key, especially for a home. When I bought my first home in Clark County in Washington, I was given a radon test, and this was 1994. So it's been around a while, and so all these tests have been done, and radon is a known issue. So it really hasn't been gotten as much publicity, I think, as other systems.
Just a few more to go. This one is asking, can you penetrate intersectioning foundation walls with the pipe and still have one fan riser for 15,000 square feet?
No, it's very clear that when you have any sort of foundation walls or any below grade or below slab separations, then you have to treat things totally separate. So no, you can't use a pipe that goes through one of those walls to an adjoining volume and treat it like it's all the same volume. It's got to be separate.
Okay, the next one question is, where does the 6-inch diameter SSESD pipe requirement come from? Per OSSC 1812.2.6 states 1, 3, or 4-inch diameter pipe.
Now, if you do look in the Oregon Structural Specialty Code, there is provisions for a 6-inch riser. I don't have chapter and verse cited here, and I don't have access to it, but I can look that up if somebody's really curious and somebody wants to drop a line, drop an email or something. I could definitely point them in the right direction.
Fantastic. How are radon systems added to existing slab on grade buildings? Do you have to bore out for the pipes underground?
So that's
I've never had a project that does that.
Yeah,
that went back.
I haven't either, Steve. Maybe one of the criteria that we should have set for Oregon and Washington, it's all new construction. So R2, R3, public buildings, new construction. Existing construction is exempt in these two states. When we were looking at the Florida code does have an appendix that is focused on existing buildings. I did not get a chance to dig into that, but I immediately asked that same question to myself. I was like, wait, if it's a slab on grade, how do you deal with that? In the Florida code, it outlined 5 different criteria of how you could mitigate radon. And one of them was to create negative pressure under the building, to create and these are separate, right? So these are like, you could do that strategy, these 5 different strategies, or you could do a combination perhaps. One of them was negative pressure under the building, positive pressure in the building, ventilate the crawl space. It's 3. Do you remember what the other 2, Steve, were? I'm trying to remember now.
No, I don't.
Anyway, I think creating a positive pressure in the building with your ventilation, I think would be the strategy you do for an existing building, because you can't.
Yeah.
It's not that you can't. It would be definitely cost prohibitive or not financially feasible to try to do something under the slab, I don't think.
Yeah, I think probably the best thing is to do the testing, right? So see if you do have an issue with radon, and then it's probably you're looking at that exemption that I talked about regarding your HVAC systems, and just make sure that you're well ventilating an existing building, you're bringing in enough outside air so that you're flushing or keeping that existing building pressurized in relation to below slab. That's probably the best thing to do when you're talking about an existing building and a slab on grade, is just making sure that those HVAC systems are sized so you're pressurizing the spaces, and radon gas doesn't have an opportunity to seep in.
And the last question I see is mat slab conditions, MAT mat.
Not sure I understand the question. You're still going to have the membrane requirements. So I think that the things we outlined would still be applicable here. Again, if it's a mat slab condition and it's under occupied space. We just finished up a project for with Interface. It was a city hall project, and it had a mat slab, and that's an interesting one, Steve. I think we were able to show the exception for the air changes per hour, but that one was garage space over the mat slab, if you will, and then the occupied space for 3 floors above.
Correct. Yeah. Just real quick, as I was going through the code, so in 1811.2.5 in the Oregon Structural Specialty Code, that's where it says each SSESD shall consist of one 6-inch diameter solid pipe. So that's where it's in the Oregon Structural Specialty Code.
If you have it open, it looks like the question was citing 1812.2.6. Is that the conductive pipes, the pipes below slab?
1811.2.6.
1812.2.6.
1812. 2.6, is that what you said?
Yeah, it looks like that's what I made reference to.
Yeah, and I think this is where, yeah, this is a passive system. That's not for an active system. So that, and I believe that this is also that section. 1812 is the residential portion for R2 and R3 occupancy. And 1811 is for the commercial or for other or general radon. Yeah. Yeah, so that's that. I don't, yeah, it talks about that, but it's mostly about the SSESDs shall consist of one 3-inch or 4-inch diameter solid pipe. And that's exactly what it says, but this is more for, it's only for R2 and R3 occupancy.
And so just reflecting back, that's what Washington says also. So it's the public buildings that kicks us into the 6-inch, and then our references. It's hard to maintain the same details with a subtle difference and making sure that people are applying the right thing. So for us, we're going to go with the worst case scenario. It's 6-inch. We'll apply that to all conditions.
Right. Yeah, obviously a bigger pipe will allow for more airflow. It's less resistance, so especially if you've got an active exhaust system, you're going to have less restriction there. You're going to get more airflow out of your system. Even if it's a passive system, the larger that riser pipe is, the better.
That's great. Well, and those are all the questions, and we've run out of time. So thank you so much for participating in today's webinar. We hope it was informative. If you have any comments or suggestions for improvements, please send us a note. We welcome any and all feedback. And keep a lookout for our next Interface Educational webinar in September on urban renewables. Thank you so much and enjoy the rest of your day. Thank you, Jeff and Steve.
All right, everyone have a good day.
You're welcome. Thank you, everybody.
Yeah, thanks. Bye.